All right, today we're going to talk about average velocity and instantaneous velocity. And they're two different things, and hopefully in your reading you already learned that the average velocity typically is over a wide range of time, and instantaneous velocity occurs at a single point. Now, average is typically pretty easy to find. Instantaneous takes a little bit more work, but it follows the same path. So we're going to look at this problem here where we have this position versus time graph of a car. It says it's moving down the highway. And we're going to answer these three questions, and we're going to see exactly how do we find the average and instantaneous. So in part A, they ask us to determine the average velocity over the 4-second time interval. So we're talking from the point right here to this point right up here. If I want to know that average velocity, we found already that the slope of the line for that segment gives us that speed. So if I go from here to here, the slope of this line will be the average velocity for that time interval. So all I have to do now, slope of the line, that'll give it to me. So V here is going to be the rise over the run, so it'll be 40 minus 10, and then divided 4 minus 0. Those are our two intervals right there. We've got when time is 4, we get a speed of 40, and when time is 0, we get a speed of 10. And we come out to see that it is 10 meters per second. So for the entire trip, this car averaged 10 meters per second. Clearly along the way it changed, but for the average trip, it was, again, that 10 meters per second. Part B now asks us to find out what is the instantaneous velocity at 2 seconds. Right, so here is our 2-second point right here. Now, we cannot find the slope just at 2 seconds because it's only 1 point. Right? And if we're going to find that slope, we need a couple points. So what we go to find right here is we do this thing we call the whisker method. And what I do is I get my point and I put two lines on either side of them that are perpendicular to the line. And once I put them perpendicular to the line, I'm going to draw a third line here that is perpendicular to those two little lines. And hopefully we can get it the way we want it to go. Something like that. This isn't the best program for doing this, but something like that. And when we do that, we then find the slope of this line. So this is the speed at this one little instant at 2 meters per second. So now that we find this slope, find this line, we find the slope now. Again, we got when time is 20, when the speed is 20, we get a time of 3.5 seconds. And when it's a half a second, right, we get that the speed is 5. Okay, I try to pick points that are on the line and they're easy. We don't want to make it too difficult. So we're just going to pick simple things where we know we can get a half, a 5, something that is very obvious. We don't have to mess with like 0.25s or if something's 13 or if it's 12.5. Make our life easy. When we do that out, we find that at that one very moment where the time is 2, it's going 5 meters per second. And if you look at the slopes of these two things, we can see that clearly that makes sense because this 5-meter slope is more shallow than the 10 meter per second slope. Okay, now for C. C wants us to compare and contrast the average speed over the last half second with the instantaneous speed at 3.8 seconds and then find the values for each. So my guess is going to be that they're probably going to be very similar, only because you can see that right at the end it is a straight line right here. So that's going to help us. So if we look at the time for over the last half second, we go from this point right here to this point right here. And if we find that the slope of this line, right, it runs right through something like that. Okay, and if we can find this average speed, again, this will be the average one. And it's going to be just V equals 40 minus 22.5. Again, you can check the coordinates to make sure they look all right. And 4 minus 3.5. And we should come out to get that we're at about 35 meters per second. Okay. Now the instantaneous, we're going to go back to that whisker method. So we're going to find that 3.8, which is somewhere right around here. Right? 1 whisker, 2 whiskers. Okay. And then we'll put our line down again. This time we'll make the line blue. Okay. And try to get right through it, kind of like that. And you can already see that it's pretty much the same exact line. And if we pick points there, right, we get that V equals, I probably should have made that line a little longer, right, 40 minus 22.5, right, get the same stuff going, 4 minus 3.5. And we should get the same speed of 3.5 meters per second. And it works, 35 meters per second. So it works this time because, again, that last little section of that graph, if you look at your paper, it's straight, so the slope is constant. So these two lines are going to have the same slope, so they're going to have the same speed, same average and same instantaneous speeds. So the next problem we'll look at will be a little different. It's going to be a velocity versus time graph. The work's a little different, but the methods are still the same. Alright, so now we move to a velocity versus time graph. A little bit different, but the ideas are still the same as we move through it. Alright, so we go here, and part A asks, determine the average velocity for the first 3 minutes of the ride. Well, if we look at the first 3 minutes of the ride, right, we start over here, and we go all the way to 3. It's the same. Pretty simple, right? So the average velocity, it stays the same. We're going to call it 1.5 meters per second. Pretty simple there. Okay, so part B says determine the instantaneous velocity at time equals 2. Well, if we go right down here, the nice thing is this is already velocity versus time graph. So we don't have to do the whisker method. We don't have to do anything special. We just have to go to where time is 2. And we see that the velocity when time is 2 is 1.5. Again, simple, simple, simple. All right, so part C, they say determine the average velocity from the interval of 3 to 4 minutes. So here we've got 3, in here we've got 4. All right, so if we want to know what the average velocity is there, we can't do the slope because the slope of a velocity to time graph is not velocity, right? It's an acceleration graph, right? That'll tell us the acceleration for this, the average acceleration for this. So it's a little different, but again, simple. You learned this a long time ago. If I want to find the average of something, I take the number of values I have, add them all up, and then divide by the amount of values I have. So in this case, I've got 2 values. Right, I've got a value of when the time is 4, it's 3 meters per second, and when the time is 3, it's 1.5 meters per second. So I just add them up, and I've got 2 values. So that tells me then that my average velocity from a time of 3 to 4 minutes is going to be 2.75 meters per second. Not too bad. Right? That's a little bit of a sticking point when it comes to finding out this average velocity for a VT graph because it's not slope, it's just calculating that average. All right, so D, determine the instantaneous velocity at 3.5. So here's 3.5. All right, so again, instantaneous, just read it right off the graph. We go across, looks to me like it lines up with 2.5 meters per second. All right, so the V when it's at 2.5 minutes, all right, I'm sorry, 3.5 minutes, my bad, gives you, again, about 2.5 meters per second. All right, and then E. E is where we make our money. All right, E says determine the total displacement for the entire trip. All right, so the total displacement, this is where things are nice. We could go through, we could do some calculations all that. There are two ways we can do this. We have all the average speeds here, and that'll help us. There's another way we can do it that I can show you after. So if we look at this, we know that speed is equal to distance divided by time. If we rearrange that a little bit, we get that distance is equal to speed times time. Right? And this is going to be the average velocity during this time interval. Okay? So if we call this section A, section B, and section C, and we just drop a dotted line down here to partition them off so we know what we're talking about. All right? For section A, we get that the average velocity from 1 to 3 we found in part A is going to be 1.5, right? And the time, now a little tricky. We've got speed in meters per second, but they give us the time in minutes, so we need to convert that into seconds. 3 minutes, 180 seconds. All right, and then we find that that distance is going to be 270 meters. For section B, we found the average from 3 to 4 to be 2.75. So we get D equals 2.75. It's for 1 minute, which is 60 seconds. All right, which gives us 165 meters. And lastly, for section C, we get D is equal to, let's see, section C lines up with 3 meters per second, so that's going to be our average for that last time interval. So we get 3 times 60, that gives us 180. So now we find that total displacement, the total distance from where they started to where they ended. We add them all up. We'll call it D sub total, and we get that it has to be 615 meters. So that's one way you can do it, and it makes sense. Pretty simple. Another way you can do it is to find the area under the graph. Finding the area under the graph will give you that displacement as well, because if you look, if we find the area of section A, it's this dimension of from 0 to 3, right, or 180 seconds, and then our length right here, right, we call it our height. It's 1.5, so 1.5 times 180 lines up with this 270, all right, and it works for the other two sections as well. So there's two ways you can do it. If you know enough information, you can do the what we did in part E, or you can go through and you can find the area under the graph. Right, two both very useful and powerful ways. So that's that for average and instantaneous. I hope that this helps. Use this information now and attack that AP problem that I gave you earlier. Good luck.